So now, introduction, I'll introduce Basilio Lenzo. He's joining us from Sheffield Hallam University.
81 now.
Out of the UK. He's actually a member of the IEEE Tellers Committee, which is the standing committee by IEEE that validates and certifies the annual election. I too was the chair of that committee, and then requested that Basilio come on down after our Tellers meeting. So the Tellers meeting wrapped up yesterday, and he stuck around an extra day for us to present. So let's see, a couple highlights from his bio. He graduated with a Master of Science degree in Mechanical Engineering and then a Ph.D. in Robotics. He was an R&D engineer for Ferrari and awardee of the MIT Young Inventors Under 35 Italy Prize. He was invited to give a TED Talk previously in 2015. He's actually told me he's got another one planned in 3 weeks. So, I mean, we got the cream of the crop here. Let's see, he's currently a senior lecturer in automotive engineering with Sheffield Hallam University with research interests in the field of vehicle dynamics and control. His recent research activity focused on the development of vehicle simulation models and state-of-the-art controllers for vehicle dynamics, energy management, and on vehicle state estimation. So, with that, please help me welcome Basilio Lenzo.
Thank you very much. Thanks a lot for being here today. So thanks for the introduction. And yeah, I'm going to start with a question actually for you, which is this one here. Roughly, how many people you think are killed in road crashes every year? Like, I don't know, 1,000, 10,000 or something. Just give me a figure. 100K. Unfortunately, it's much more than that. Obviously, we're all aware that there are vehicle active systems such as the ABS or ESC that help us, let's say, to some extent. I guess you're all familiar with ABS and ESC. ABS is the anti-lock braking system. Let's say it reduces the stopping distances and keeps vehicle steerability. ESC, electronic stability control, prevents unintended, let's say, potentially dangerous lateral behavior. If you look at figures of estimated lives saved by this kind of system, in particular ESC, you'll find that the ESC saves roughly around 2,000 people per year, which is great, obviously. But if you look at, again, the amount of people that unfortunately die every year, that's much more than that. So what's the point? These systems, like the ABS, the electronic stability control, they do what they can do based on what they know about the vehicle. So with states, we mean key parameters of that represent the vehicle motion. An easy one, the vehicle velocity. Some others are less easy, less straightforward, but they would tell us a lot. So what's the idea? If we could know more about what's going on with our vehicle, we could do much more than the electronic stability control. And the main idea is that, I want to say something about ESC shortly, but if you look at how it works, essentially the electronic stability control intervenes, so it is triggered when it detects that something is not right. So it corrects a potential dangerous behavior of the vehicle. But when it does so, things are already not good, if you know what I mean. Well, if you knew, so if we could be able to know everything about the vehicle and not just what we are able to know so far, we could actually intervene and anticipate loss of control situations rather than like reacting to them. And to show you some of the things we can do potentially. I will start talking about vehicle dynamics control. In particular, I'm going to introduce the idea of torque vectoring, which is actually a very simple idea. Literally, like, what it means is, as you can see there, individual control of wheel torque. So, ideally, I could, again, decide what's the amount of torque that I'm sending to each wheel, each corner, right? And to some extent, this is already happening, but there's much more potential there. Where does that happen? What's that? Controllable friction braking torque on individual wheels. That is already happening in your cars now. Well, hopefully it doesn't, but if it does, if it is needed, it's there. And again, that's the electronic stability control, right? So if it detects there's something not right, it will brake a single wheel, right? Why? To compensate, let's say, either excessive understeer or excessive oversteer. And how does it do that? Well, it compares relevant states of the vehicle. In this case, a simple example could be the yaw rate of the vehicle and the steering wheel input from the driver. If they're too much different, it means something's not right. So, like in the top one, for example, here, what we see is that if there's understeer, so the vehicle is going nearly straight, or at least is not cornering as much as probably the steering wheel angle input would tell us, before the ESC says, right, I'm going to brake a rear inside wheel so that I would produce a compensating moment, a yaw moment, that would help me correct my course, right? And vice versa, obviously, in a case of oversteer. Not sure you're familiar with that, but that's something that, again, takes place whenever needed, but in your cars already. Well, obviously, and we'll come back to this, since you are applying a braking force, you're reducing the vehicle velocity. And we'll come back to this. Is there another way to achieve torque vectoring to some extent? Yes. Limited slip differential, for example, right? Limited slip or closed differentials, as long as it's not an open differential, the torques that you send to, let's say, the left and right shafts are different. Thing is, this is a mechanical system, obviously. So there are some sort of constraints you got to satisfy, such as more torque will go on this lower wheel of the axle here. Is there another option to achieve torque vectoring? Yes, that's the most, say, recent one. And guess what? Electric vehicles with multiple motors. So if I've got, like here, for example, I got 4 motors, but even just maybe 2 on the same axle, well, I can do torque vectoring by definition. Like here, I've got 4 motors, so I request whatever amount of torque I want at each of them, and there I go. I've got, again, the amount of torque I want at each corner of the car. And you see here, there's not really constraint, like, for example, in the differential. Like, so I can send, like, more torque on the faster shaft or vice versa, or whatever. Obviously, it is an over-actuated system. What does that mean? Well, clearly, in a standard car, internal combustion engine car, you push your throttle if you got 1 motor to satisfy your request. But if you got more than 1, well, you got some freedom, right? So you can make the most of it. And we'll see how. In particular, when it comes to electric vehicles with multiple motors, I would say you can do mainly there's 2 main things you can do with torque vectoring. So you can, on one side, focus on energy efficiency, and on the other one on, say, changing the vehicle dynamics. So, energy efficiency wise, what's the idea? The idea is pretty simple. I've got to generate a certain traction force or braking force. That depends on my pedal positions, right? So the question is, since I've got multiple actuators, where do I send the torque? For example, here you see that there's maybe more at the front than at the back, maybe 70-30%. So is that optimal? Or maybe the best is 50-50, or maybe 20-80, or what? In order, again, to maximize the efficiency of the system. On the other hand, here, if you request more torque on one side of the car compared to the other, what happens? Well, like here, right? So there's more on the right side than on the left side. Well, you generate a yaw moment effect, right? It's a yawing effect. It's called a direct yaw moment, MZ. So that what you are able to do is to change the response of the car, the dynamic response of the car. Whenever it comes to torque vectoring, if you look at the papers, if you look at patents in general, the typical control structure is more or less all the time is the same, kind of the same, and it looks like that. So there's three main layers, and I'll quickly go through them because it's important to understand what's really going on there. So we've got layer one. So in there we need to define a target yaw rate, reference yaw rate. Okay, so somehow, I'll quickly tell you something about that shortly, but I need to say, right, based on my steering wheel input delta, steering input from the driver, the longitudinal acceleration AX, the vehicle velocity V, in real time, I work out what is my, again, reference target yaw rate for the vehicle.
So that, excuse me, that's
Sure.
basically how far he's turned the steering wheel?
Not really. Well, let's say, in principle, you could say that the reference yaw rate could be potentially like a constant times the steering wheel angle. So it could be an option. What we're going to do here, we're going to show you, is something more complicated. But to some extent, I'm not saying it's proportional to the steering angle, but in a very simple version, it could be. So then you've got your reference yaw rate, and then you compare that with R, which is the actual yaw rate of the car, which you measure with, for example, with an IMU, right? An inertial measurement unit. Tells you what's the acceleration, and by the way, and also the yaw rate of the vehicle. So what comes out of this is an error, right? The difference between your target value and the actual value. So what you do with this error, we are in layer 2, and essentially you deal with it by introducing a control law, which could be a simple PID, which I guess you're all familiar with. It can be something more complicated, like an H-infinity controller, or actually whatever you want, really. But the thing is, I've got an error here, which is a yaw rate error, and I end up with a desired yaw moment, which allows me to follow the reference value of the yaw rate. What else is here? This F, and that is the target force. So that depends, to keep it simple, just on the brake, on the brake and accelerator pedal that are controlled by the driver. Right? So based on that, I know that I want to accelerate this much or brake this much. So the output of layer 2 are two numbers. What's the force that I want? What's the moment that I want? Right? So then I've got layer 3, and what's in there? Well, in there I need to translate, to some extent, if you want, you know what I mean, these two numbers into, well, in this case, 4 numbers, which are nothing but the 4 torques, the 4 torque demands, right? So at each corner you want this much Newton meters so as to generate this force, this yaw moment. Obviously, there's some freedom there as well, right? Because from 2 numbers, you want to get 4, right? If you compare this general like framework to the electronic stability control, one of the main differences is that this is working all the time. While the ESC, like we said, intervenes when only like in safety critical conditions. So I'm gonna focus right now for a while on this aspect, right? So if I ask for more torque on one side of the vehicle compared to the other side of the vehicle, I've got a yaw moment that is generated. And what do I do with that? What can I do with that? Let's have a look at the cornering response of the car, which I actually, turns out, I can design it. But what is it, first of all? Think about, to keep it simple, so you are on a circular trajectory, right? And you're all the time there, but you accelerate, right? So going from, say, 20 to 100 kilometers per hour, and you stay on the same circle. So as you increase your speed, what do you expect to happen to the steering wheel? So you stay on the circle, but you go faster and faster. What happens to the steering wheel? How much? More, less, like stays the same, it goes, it increases, decreases. What do you think?
Wouldn't that depend on whether you're in an oversteer or understeer kind of situation?
It would, yes. And since a standard passenger car is understeering, because of that, that would increase, if you think about it. So you would need to increase the steering wheel input as you increase the vehicle velocity. So if you plot the steering wheel angle as a function of the lateral acceleration, what you get is normally you've got a linear behavior, sorry, then up to like 4 or 5 meters per second square, g is gravity acceleration. And then at some point it's non-linear, and finally there's an asymptote, and that's it.
Then you're drifting.
Sorry, and then you drift. What can you achieve potentially with torque vectoring? Well, you may decrease this slope, which by the way is related to the concept of understeer that you've mentioned. You can increase the linear behavior, and this is an important one. You can actually also increase the maximum achievable lateral acceleration, essentially because you are, in this case, moving towards a more neutral, what is called a neutral vehicle. And if the vehicle is closer to being neutral, it means that you're making the most, or you're getting closer to making the most of the two axles in terms of force availability. So if you got more force, second Newton's law, right? F equals ma. If you got more force, you got more acceleration. Now, I'm not going into the details because we haven't got much time. But the thing is, my baseline vehicle looks like this, something like this, depending on the longitudinal acceleration. And what I need to do here is to design whatever my target is, right? And this is not big deal, it's just an analytical formulation of these curves. So whatever you want, you actually need to describe that analytically, right? So here there's no big deal going on, so it's a line, a still AY star, which you decide, again, as an engineer here, and then it gets exponential. But that is an example, right? I'm not saying you have to do that. I'm saying you can design your vehicle cornering response, right? So once you've done that, you get into a, say, procedure that you've got to follow. Again, I'm not going to the detail of that, even if I'm happy to talk about that afterwards. But the concept is, if you remember that block, a green block we mentioned before, reference generator in the first layer, layer 1, well, that is, in the end, it happens to be just a lookup table that indeed, based on the steering wheel angle, vehicle velocity, and longitudinal acceleration, provides you with the reference yaw rate. And here is how to build it. I'm not going through that, but it's essentially very simple. You use steady state equations for the, let's say, vehicle equilibrium equation in steady state conditions. you use your defined target cornering response and then some basic kinematics. In terms of control, like I said, you can use a PID controller and keep it simple. Actually, most of the time it works pretty well. You can have different formulations, fine, like sliding mode control, like I said, H infinity or anything. But in the end, you'll end up with a yaw moment, the target yaw moment, to follow the target yaw rate. What I'm showing here is some examples. We've got here the baseline vehicle, which means the vehicle where there is no yaw moment, right? And what we call a sport vehicle, which is obviously the one we've designed. It's called sport because it is less understeering than the baseline vehicle, or if you want, it's a little bit more oversteering. Even though the target cornering response is designed in steady state conditions, like I said, you do get benefits in transients. And we see an example here of the yaw rate resulting from a step steer maneuver. What is a step steer maneuver? You're going straight, say 100 kilometers per hour, and then all of a sudden you apply a steering input, roughly at 400 degrees per second, so a very quick one, and you keep it, and you see what the car does, right? So if you look at the transient behavior then that you've got here, what you see is that the controlled vehicle is much better in terms of, indeed, you see that transient response. So the oscillations of the control vehicle are much, let's say, better. So let's say they're less than in the case of the baseline of the passive vehicle. So the concept again is, even though the whole thing has been designed in steady state conditions, you do get benefits in transients as well. Right. What we've been talking about so far has to be better defined as handling yaw rate, which is nothing but what we've seen before, right? So the target yaw rate based on my handling requirements, right? Thing is, you might have noticed that there was a mu in those formulas there. What is mu? Is the friction coefficient, which is not easy at all to know in general. Friction coefficient estimation is a challenging task, is a difficult task. Thing is, if you have such a control in your vehicle, but the friction coefficient you've got is not the actual one, so you are in a perhaps low friction condition, and you don't know it, the car doesn't know it, things may get really dangerous, and we'll see that later. So what's the thing? Since estimating the friction coefficient is difficult, we found like kind of workaround, an alternative solution, which is to use the vehicle Sideslip angle, which is the state of the vehicle. And what is it actually? For those of you who do not know, it is simply defined as the angle between the velocity vector of the center of mass of the vehicle and the longitudinal axis of the vehicle. So that angle is the Sideslip angle, very often indicated with the Greek letter beta. Obviously, when you're going straight, that's 0. But whenever you're not, it's there. It's really small, normally, a few degrees, but it's there, and that's a really important parameter. So, what did we do? Like I said, Sideslip angle is normally pretty small, and it gets big when things get critical, such as if you're about to spin, for example, or lose the vehicle, well, this parameter will get significantly bigger than a couple of degrees. So the idea was, let's introduce this parameter in our controller. So what we see here is exactly the same concept as before in terms of layout, framework, but there's an extra block here, which is simply a correction block of the yaw rate. So before I said just reference yaw rate, then I said, let's call that handling yaw rate. Because the actual reference is not going to be just that, but it's going to be a correction block in between. All right. And what does this block here. What does it do? Well, simply it looks at what's the sideslip angle, and simply speaking, if the sideslip angle is small, no issues there, so it's not doing anything. So this F will be 0 if the sideslip angle is small, less than an activation threshold. So if this F is 0, I got that my reference yaw rate is equal to the handling yaw rate that comes from here, which is the same as was going on earlier. But if the sideslip angle is either within an activation or an upper threshold, or even beyond a threshold, then this F is no longer 0, so it does make a difference here, and essentially it decreases, so it corrects the reference yaw rate, it decreases it based on the sideslip angle, and we call that a single input, single output formulation, because differently from other controllers, it gets a single input and a single output instead of having, in particular, multiple outputs in terms of yaw moment. So what you see in the literature, what you can see in the literature is that there's a yaw moment contribution that looks at the yaw rate error, and a yaw moment contribution that looks at the sideslip angle error. But the other thing is, these two things, these two effects are, let's say, one against each other, so it's not easy to control them. So what we do here is we correct the reference yaw rate based on the sideslip angle, so that we got a single input here, the error, and the single output, just the yaw moment. RS here, what we call a stability yaw rate, and essentially it is a measure of what is actually achievable by the vehicle in terms of yaw rate. That indeed it depends on the actual acceleration and the actual velocity of the vehicle, plus some tuning parameters. Another point I'll quickly go through is where should we measure the sideslip angle, or what point should we use as a reference for the sideslip angle? Because normally you would look at the center of mass, like I said before, right? So we call it BCG, center of gravity. But assuming, as often it is done, that the vehicle is a rigid body, then you can potentially look at the sideslip angle anywhere else. And in particular, we found that if you look at the sideslip angle at the rear axle, things work better. And long story short, the reason is simply that there is no kinematic contribution unless the vehicle is, let's say, if the vehicle has no rear steering capability, there is no kinematic contribution if you look at the sideslip angle at the rear axle. A simple example is parking maneuver. Parking maneuver, you're going really slow, so there's no many forces there, the slip angle is small, but the steering angle is big. So if you would look at the sideslip angle, let's say here or there, that would be big, but it would be big just because the steering angle is big. It's a kinematic, it's an intrinsic thing. It's a geometrical effect. So you can't really correct it because it's there. What you need to correct is the dynamic contribution.
Question?
Sorry.
On that beta calculation, is that determined dynamically as the car is going down the road? And I'm thinking specifically maybe changing road conditions, you go from good road to where you get some slippery. But if you're going straight ahead, you may not notice that unless you introduced some steering input to be able to calculate the beta, right?
Thing is, if you're going straight, beta is 0. So you have no potential like lateral instability issues. Yeah, and you wouldn't, well, at least by looking at the sideslip angle, you wouldn't figure out what's going on in terms of friction, yes. But actually the slip, the longitudinal slip of the wheels would be different. But that's another story. But here we're looking at lateral stability, but that's definitely a good point. I thought it was worth to quickly mention this tool, which you might be familiar with or not, just a whenever you deal with a dynamic system, really. So that's why I put it here, not just vehicle dynamics. It's phase plane analysis, where you put two relevant quantities, in this case, the size-slip angle and its derivative. What happened here? Blue points are a set of initial conditions. So we've run quite a lot of simulations here. And then, obviously, the red lines describe the evolution of the system. What we wanted to show here is that without this correction based on the size-slip angle, there are initial conditions, quite critical one anyway, for which the system essentially is unstable. So what it means is, in our case, you lose control of the vehicle, right? Whilst what we show here is that with the contribution that we've mentioned earlier, well, the points that were stable are still stable, obviously, and the points that were not stable do become stable, and they got around this point here, which is actually, like I said, tunable by the engineer. It's what I call the upper threshold of the size-slip angle. So why did we do this, by the way? Just to see that, at least in simulations, things were working. Because later on, we tried it on the actual car. And what's the car? Sorry. The car was a Range Rover Evoque that was, so this research was carried out within the European project I composed. So one of the partners was Jaguar Land Rover, so they provided us with a car. It looks like a common Range Rover Evoque. It is not, because inside it looks like that. So it is an electric vehicle prototype, so there's 4 electric motors on board. As you can see, motor 1, 2, 3, 4, there's a transmission, then inverters. We're in the UK, so the steering wheel's here, a big battery pack, and I1, 2, 3, 4, the inverters. Here you can see the main parameters. I would just focus on maybe on the torque, which is quite big. We had 80 Newton meters nominal, but with a gear ratio of, say, around 10, that means we got 800 Newton meters per wheel, which is quite a lot, and overall it is 3,200 Newton meters for the whole vehicle nominal. It's quite a lot. We had a vehicle control unit based on this space, so we could deploy our control techniques developed in MATLAB Simulink via this space and using the this space order box. Somebody mentioned drifting before, so potentially we could not just bound the size-slip angle within whatever threshold, but also maybe have these thresholds relatively high, but maintain the vehicle within those thresholds, so achieve a controlled drifting behavior. And you can see here that when we set thresholds to like 6, 14, 20 degrees, we actually achieved size-slip angle that was bounded within 6, 14, and 20 degrees. Another test we carried out is slalom on a low friction area. That one here. A couple of tests, one on line 1, so high friction and low friction, and then high friction again. One on line 2, so it's a continuous sort of mu split condition.
Just curious, do you want to try turning that mic off?
Yeah.
Maybe just use it.
Yeah.
I don't know if that's
I think it was because I was doing this. Might be okay, but let me. So I want to switch this off. Just see that one. So what we can you hear me? What we essentially see here is that in terms of size-slip angle, well, first of all, the active vehicle, IV, active, but without correction, is worse than the PV, the passive vehicle, with no yaw moment at all. And the reason is, like I said, in here, the torque vector in control is following a reference yaw rate that depends on the friction coefficient, but actually the friction coefficient that is used is not the actual one you got when you're driving, and we'll see that later as well. In terms of FA, CG, RA, so this is back to what I said earlier. If you take a side-slip angle at the front axle, at the center of gravity, or at the rear axle, essentially you see that the rear axle is better. So it is bounded in a smaller range. Here we can see what happens in terms of yaw rate. For just three tests, baseline vehicle, passive vehicle, yaw rate only, and yaw rate plus side-slip angle correction. Here you might see that 60 degrees per second is a lot, and actually we lost the vehicle there. So you see we lost that with the controller and no correction, but we didn't lose the vehicle with the baseline configuration. Side-slip angle wise, again here it goes much negative, so definitely a big value. The low friction area was between 4 and 9 seconds. This is the first test, so high friction, then low friction, and high friction. There's not really much time to talk about these performance indicators, but it might be worth to have a look into that. Most of them are quite standard, like the root mean square error. So essentially we had to quantitatively assess what was going on there. There's not much time for me now to go through them. ESC logic, like we said, the electronic stability control intervenes only when it detects that something is not right. So we implemented a basic electronic stability control logic, and we compared that with our controller. And what we found essentially is that since our controller, again, is active all the time, essentially, it happens to be better than the electronic stability control, which obviously is better. The electronic stability control is better than the passive vehicle, but the continuously active controller is even better. Right. Yeah.
You had no sensor on the trailer, that's just the back end of the vehicle?
So we had an accelerometer on the trailer, but we didn't really use that for the control. The only thing we measured was the hitch angle. So again, the misalignment, and we did that by...
Sorry, what did you measure?
The hitch angle, so the misalignment between the car and the trailer. So if they're like, this angle here, like 90 degrees say, or 0. That's the only thing we measured.
So you weren't doing any braking on the trailer?
Sorry?
You weren't doing any braking on the trailer?
No. We just attached the trailer. We were not controlling that at all. No. Just controlling the 4 motors of the Range Rover Evoque. Right. So this is what we've seen so far is the first part, right? Like I said, direct yaw moment control can do lots of nice things, as we've seen. The other aspect I'll quickly go through is, like I said, energy efficiency. And it boils down essentially to this layer here, layer 3. So once I know what is the force at the moment and what is the moment that I want, the thing is, how do I distribute the torque between the 4 motors? Actually, there's no time to talk about that here, but actually it's not completely true in the sense that you could actually work on this one as well. So if you disregard just purely vehicle dynamics criteria, and you just say, and you ask yourself, can I find the optimal yaw moment in terms of energy efficiency? Well, you can. There's a paper, but I can't go through that right now, but we can do that. Anyway, here we assume that the force is given, the moment is given, so we are just here. It is very easy to show that if the steering angle is small, which is quite reasonable assumption, steering angle at the wheel is small, and the vehicle tracks are the same, which is also fair, a fair assumption, then you can, it's very interesting, you can separate the torque demands per side, which means that this is the left side torque demand, this is the right side torque demand. Actually, if you look at this formula, it's pretty easy to see that, like, let's say there's no yaw moment, so you just get half of the force on either side, and R is just the average rear radius. So this is in terms of torque, right? Force times radius. Either is yaw moment based on the conventions we used. This plus here is more on this side than on the other side. And D obviously comes by, you know, geometry and definition of moment. So the problem reduces to, I've got this much torque I want on this side of the vehicle. How do I split that between my front and rear wheel? And we call that control allocation, CA problem. To understand, let's say, what was the best thing to do, what we carried out is a large campaign of experimental tests on a bench that is called a rolling road. Essentially, the vehicle is there, but there's two rollers, one for the rear axle, one for the front axle. So the vehicle is there, but actually everything is moving, so you can ask for whatever amount of torque. You can set torque and speed and see what happens. In particular, what we measured there was the, as you can see here, the drivetrain power loss. And how did we measure that? Well, we had the voltage and current that went through the battery. So voltage times current is power. And here at the rollers, we had an information of the force and the velocity. Force times velocity is power. So we had power input, power output. The difference is what you lose in between, right? And it is what we plot here. So the power loss is a function of the torque demand and of the vehicle velocity. It's rather obvious, or let's say we expected this to increase with the torque demand, to increase with the vehicle speed. What is less obvious is what's going on here. And I'm going to show you this one to make it simpler to understand. Suppose we've got a behavior that looks like that. So the power loss, suppose it's just concave, it's just like that. So the thing is, I've got two motors, right? So let's say on the left side, 100 Newton meters. How do I split them? But if the power loss curve looks like that, there's no reason to use two motors. I just use one. Suppose let's say I'm 100, I said, right? So suppose I'm here on 100 and I get this power loss. Why would I use, for example, two motors, 50 Newton meters each? Because I would lose, instead of this, I would lose twice this. So definitely not the right thing to do, right? On the other hand, other way around, right here, if the behavior is convex, things will swap, right? So why would I waste this much power when I can lose, I lost my, why this much when I can lose twice this? Twice this is less than that, right? Thing is, what have we got here? Actually, both of them. So what does that mean? If you think about it intuitively, there will be a range of torque demands for which it's better to use a single motor, and after some sort of switch in torque, it is going to be better to use a sort of 50-50 allocation. Actually, it turns out to be like that. If you look at the efficiency maps, so efficiency is obviously power output over power input as a function of the front to total torque ratio. What is that? 1 means front wheel drive, 0 means rear wheel drive, 50-50, and let's say here 0.7 would be 70% front, 30% rear, and so forth. Look at one value of speed, like here. Low torque demand, the curves look like this, so it's better to stay either here or here. At some point they become flat, and then the behaviors will flip, so it will be better to stay here. So the value at which these curves are, let's say, more or less flat is what we call a switching torque, right? So you switch from, it's best to have a single axle, or actually it's better to have a 50-50 even distribution. We worked out the values of the switching torques as a function of the vehicle speed, and we ran a series of driving cycles. I guess you're familiar with what a driving cycle is, but essentially it's a speed profile, right? Going straight, you gotta follow a speed profile. Some pretty well known, I think, are the NEDC, like New European Driving Cycle, the UDC, there's plenty of them out there. This is one we came up with, Surrey Design Driving Cycle, and the reason was, maybe I got some time. The reason was this, if you look at the NEDC, if you know that this cycle is quite a mild cycle, it's not really demanding. What does that mean? You nearly all the time, like here, below this curve, because again, torque demands are not huge. So if you are always, or nearly always below this curve, it means that the best thing to do is nearly always use a single motor. So the advantage of using a control allocation with respect to the single axle distribution, yes, it's positive, but it's not that much. So on the other hand, what we did then is, let's simulate a cycle but with an 8% slope. What's the reason? We get, this time we get generally high torque demands. So we generally end up here, right? In this area here. But if that happens, then it means that the best thing to do is nearly all the time the 50-50, the even distribution. And indeed, if you look at the benefit of our control allocation compared to that, again, it's there, but it's not that much. So what's the rationale between the cycle here? You see that here. So we designed the cycle such that we could actually see the benefits of our control allocation with respect to both the single axle and the even distribution. So here, energy-wise, not time-wise, but energy-wise, you're nearly like half of the energy spent in a single axle configuration, half of the energy in the even distribution configuration. And you can imagine that the even distribution configuration, for example, is used like here, because this is a quite strong acceleration, or even here. So if the torque demand is high, I'm here, so I use an ED. Vice versa, these areas here, especially these ones, low torque demand, so I'm here. So here we can see both a reasonable benefit with respect to both single axle and even distribution, this torque allocations. Very quickly, we also validated this in cornering conditions. So the whole thing was designed in straight line driving. But we wondered, what if we try that in cornering conditions? It might not, well, it won't be optimal for sure. It might be suboptimal. But actually, it turns out in some conditions, it does make a difference, like, as you can see here, a few percent of energy saving. There's not much time to go through that more in detail. You might have noticed that earlier on I've been using the Sideslip angle value. Remember, that was this angle here, right? Between the overall vehicle velocity and the longitudinal axis of the vehicle, right? But how did I get that? Well, in our case, we had a prototype and we actually measured that angle using a sensor that is called a Datron, Corsis Datron. There's a couple of sensors, 2-3 types of sensors, but essentially they all do the same thing. They measure it. Well, you know, the downside is this sensor costs like more or less 15,000, 20,000 euros or pounds, more or less the same. So that's obviously a lot, and you cannot put that into a standard passenger car, right? Yet you've seen just one example of how powerful the knowledge of that parameter would be. I remember the opening slides, right? If we know more about vehicle states, we can do much better. So the final, few minutes will be on state estimation, like I said. In particular, I'm going to focus quickly on the Sideslip angle, just because we talked about that, but there's many other states that are relevant, and like I said, their knowledge would allow us to dramatically improve vehicle safety. And by the way, if you think about, I'm sure you've heard of autonomous vehicles, right? Sooner or later, they'll be mainstream, who knows when, but you know, they need to know very well what's going on around them, right? They need a very precise understanding of the environment around them. But you also need to know what's going on with yourself, right? With the single vehicle. And so right now, we don't know much. When it comes to the Sideslip angle, we can either measure that, like I said, but it's so expensive. So this is the motivation for, estimation techniques. So ways to work out what we need, Sideslip angle or other relevant vehicle states, without a sensor. So sometimes you can measure them, but maybe it's too expensive. Sometimes you can't even measure some states. What's the issue there? What's the challenge? Well, it's not straightforward. It is difficult. There's plenty of research on that, but nobody's found the ultimate solution, if you know what I mean. We are, I'd say my group is one of the groups that is trying to do that. You might have heard of observers. You might have heard of Kalman filter, perhaps. Some yes down there, so that's good. So how does a Kalman filter work? Because in the end, that's the same thing I'm going to talk about right now. You have a model of your system, whatever it is. In our case, it's a vehicle, but it can be anything. And you've got some measurements available. So what you do is, based on your model, which can be really accurate, or maybe not too much, so there's some uncertainty there. Anyway, based on your model, you work out what your states might be. But based on the measurements, you're able to correct your predicted states, let's say. And by properly, there's a lot there, but properly, let's say, weighting between what comes out of the model and what comes using the measurements, then you work out your actual estimate. And what I'm going to talk about here quickly is a technique which is not a Kalman filter. It's a particle filter. You might have heard of that, but I'm going to quickly tell you what it is. And yeah, and this is the vehicle where we've used, because we got a collaboration with the DLR. You might know that as the German Aerospace Center. They've got this vehicle platform, which is a by-wire electric vehicle. There's one motor per wheel and also one steering actuator per wheel. So it's quite an interesting platform. So there's not much down there. Essentially, like I said, we need a model of our system. That's the model of the vehicle. Actually, quite a simple one. So let's get the concept there, right? And we model it in this case, to keep it very simple, as a bicycle. That's quite common in vehicle dynamics, even if very often not appropriate. Anyway, you model the vehicle as a bicycle. So just you collapse two wheels on a single axle into one. What's in here? Essentially, F equals ma. Simple as that. V and R are the lateral velocity and the yaw rate. Here, the derivatives are here, V dot, R dot. So there's the dynamics of our vehicle. Equilibrium, you need congruence equation and constitutive equation, which I'm not going to talk about right now because there's no time, unfortunately. But what you do normally is you convert those equations into discrete time equations, where x, again, is your state vector, so what you'd like to work out of this. And this is the measurement vector that contains your measurements. A couple of words about the particle filter. It is an estimator, okay, that is based on Monte Carlo simulations. So you might imagine that you need a quite good number of particles, right? Not just like 2 or 3. It is much better for some reason compared to Kalman filter. Say there are essentially several assumptions that you have to do, you have to make with a Kalman filter are not needed here. So it is a broader kind of framework, more general.
It's still linear, isn't it? I mean, what's the difference?
No. Well, even the Kalman filter, if you use the extended Kalman filter or the unsended Kalman filter, you don't need a linear representation of your system.
But your differential equations were linear on the previous slide.
No, no, not really, because actually one of the states is the lateral velocity, and it appears like here, for example. So no, it's not linear.
Okay.
But that's a good point, because if this is linear, let's just use a Kalman filter. So no, it's not linear. And actually, the particle filter is better than, often turns out to be better than, like I said, extended or unsended Kalman filters. Quickly, what you do is you start with a set of particles. What are particles? Potential states. So maybe the lateral velocity is this much, your rate is this much, that's a state. Maybe it can be this much and this much, that's another state. Sorry, that's another particle. They're all particles. You got, say, 1,000 particles, so 1,000 potential vehicles that evolve according to your model. All of them evolve, so for all of them you can predict what the measurements would be. And then you compare those measurements with the actual measurements. So for all the, let's say, all the 1,000 vehicles, ideal vehicles, you work out what's the difference between the actual measurements that you got on your vehicle and the measurements you would get from those ideal vehicles. And then you need to define a likelihood function that simply tells you how likely it is that that particle, that vehicle is actually the one. Or maybe that, or maybe that. And then you essentially weight all the particles according to this likelihood function so as to work out your actual estimate. How now I'm running. Long story short, it worked. On several maneuvers, sinusoidal, excitation, and so forth. We had an IMU, a Datron, correlate Datron sensor, like I said, to measure the Sideslip angle, so we could compare our estimate with the actual Sideslip angle because we were measuring it. Remember, all wheels could steer, so in this case, the sinusoidal steering input was for the front and the rear wheels. You see the plot here. What comes out only from the model, what comes out from the particle filter. And things did work, like I said, quite well for all the maneuvers. We ran there's no time for that. We ran an assessment performance, but the concept again is, like I said, we need 1,000 particles, or maybe we need 10,000, or maybe we can do with 100. Because obviously, the computational time can be an issue, right? Especially if you want a real-time application. If you want this thing to run on a vehicle in real time. So essentially, we worked out an analysis, and we essentially saw that, in our case at least, with 100 particles, things were quite good. So these are the maneuvers. This is the root mean square error on the Sideslip angle. So we see that between 1,000 and 100, things didn't change much in terms of accuracy. Time-wise, there was a big difference. So better 100 than 1,000 in the end. If you move to 100 to 10, well, performance-wise, things are a little worse. That's inevitable. Running time gets less, and at least in our case, comparable, less to the duration of the maneuver. So that's, that opens a potential real-time implementation. Because the error was always within half a degree, which is reasonable. Sorry for rushing through the final part. I hope I gave you some message. If you want to know more, you can email me anytime, or you can, you're welcome to have a look at some of these papers we've published. This is the last one about these particle filters that was presented at one of the most important vehicle dynamics conferences at the IEEE 2019 in Sweden this year. But there's plenty of other papers. But like I said, I'm really happy to take any question right now, but also to discuss whatever you want, and you can just email me anytime. Just to let you know where we are, middle of the UK, Sheffield. Thanks for your patience. Thank you.